So I'm going to be presenting our work, Repurposing Segmentation as a practical LVI-NULL mitigation in SGX. This work with my colleagues, Andreas Kogler, Claudio Canella, Michael Schwarz, and Daniel. So I'm going to be unpacking this title over the course of this talk, and we're going to start with a bit of background. So you already know who I am now. So the initial motivation for this was that there were mitigations for LVI, and then there were CPUs where LVI was no longer a problem, but LVI-NULL still was. But the mitigation stayed the same with these types of overheads, so in the hundreds to thousands of %. So we figured, specifically for LVI-NULL, there's probably something that we can do that's a bit smarter, a bit better. Okay, so let's go into very quick background. So transient execution. Modern CPUs do a whole lot of things all at once, and that's because they have a lot of execution ports, and when you can pull in a lot of instructions at the same time that don't have dependencies and fill all of those execution ports up, you get a massive advantage in execution. But of course, when you do things out of order, that means that sometimes you'll have a mistake, a fault or something in an earlier instruction that happens at the same time as something else that's later is executed. So in this case, the CPU simply, at least in principle, rolls back to the mistake and then either tries again or issues an error to fix that, and then continues executing from there. And these instructions, the ones that disappear because of this, are what we call transient. So from an attacker's perspective, what is there to do with those if they're undone? And the answer is simply that the state isn't entirely removed. There are still some traces of these transient instructions that remain in the microarchitectural state. And one of those you've probably heard a lot about already at USENIX here is stuff in the cache. And so we'll take a quick look back a few years to Meltdown as an example of this, where we try to access a kernel address, which is of course not allowed, but almost at the same time, we use this value that we shouldn't actually get back to access something in our own memory. And because these things happen at the same time, and the second instruction can run before the fault of the first one is actually raised, we still get this load in our cache that we can detect later, and with that we can get out the value. And so now Jo van Bulk had the idea 2 years ago, or 3 years ago, that we can actually turn this around. And instead of leaking, we insert a value. And so from the exception perspective, that means instead of generating an exception in our process and then leaking something from the victim, we try to generate an exception in the victim process and get one of our values to leak into the victim. And then transiently, we can, if there's a suitable gadget, make the victim give up its data. And then we can get it out with the cache, as is fairly usual for all of these papers. So a question for LVI-NULL might be how these values actually get injected there. But for this talk, luckily, it doesn't really matter, because at the time, Intel had already fixed this on newer CPUs, and there were no more values injected. But these CPUs at the time still injected a 0 instead. So where before there would be a value leaking from some buffer, now it would be just 0. And something that Jo van Bulk already recognized at the time is that this doesn't actually solve the problem, because with zeros alone, you can still do a whole lot. So I don't know if you can read this very well, but I'm going to go through it quickly. So we categorize this into several types of injections. Those are gadgets for control flow and data flow. For control flow, we have direct jumps, where we can inject a 0 into a function pointer, and then that would execute on page 0. An indirect jump, where we inject a 0 one step earlier, and then the target address would be loaded from address 0. Then we could construct a transient stack. We could influence branches. So if variable, if we inject a 0 there, we can change direct loads directly to 0. This is something that Jo used to break AES, for example. And then we have, lastly, indirect loads. So let's look at two of those more closely. So for the indirect jump, we have something that you can imagine like vtables in C++, where you first have the address to the vtable, and then the vtable has the pointer. So if we inject a 0 into the first load, then the vtable will be expected to be at page 0. And if that is under attacker control, the next transiently executed instruction will be wherever the attacker wants. And for the indirect load, you can basically inject arbitrary values after one level of indirection. So what you might notice here is that this needs the 0 page, which is not something that is usually available. Firstly, it's not mapped. And secondly, why would an attacker have access to the 0 page of a victim process? Doesn't usually happen. So this is where our lovely threat model of SGX comes into play. You're going to hear a bit more about SGX, I think, later this session. So let's make this quick. The threat model is that SGX protects the enclave from the operating system. So we have a way of securely transitioning into the enclave with the EENTER instruction. Then the enclave does secure computations, and then we return to the untrusted world. And the operating system is not supposed to have any way to read the memory, their write memory, and all of that stuff should be protected. But the operating system still has control over some parts of the page table entry. And one of those parts is the bit about access. So if a page has been accessed. And if we clear that bit, that is actually one of those types of faults, or a microcode assist, that generates one of these injections. And again, building on something from Jo van Burg, with the lovely SGX step framework, we can actually step the enclave to a precise instruction where we want to inject the fault, and then set reset this access bit, and then let the enclave run forward, and we'll have injected a 0 exactly at that point. So we wanted to mitigate this. Finally back here. So that's a problem. An attacker can inject zeros. The standard mitigation was inserting fences everywhere, and we saw that the performance is horrible. So instead we thought maybe we could approach this problem from a different direction and allow the enclave to control where this actually goes, where these 0 loads go. And our solution to this was to make all loads in the enclave relative to the enclave beginning, or to a part of the enclave beginning. And for this, we thought of using segmentation. So in x64, segmentation is almost gone. There are still 2 segment registers that are available for general use. It's FS and GS. And we discovered that in SGX, those are mapped to the same value, and we can free up one of those. And so now what we do is we place this GS base address somewhere in the beginning of our enclave that is part of the attestation, so it can't be changed by an attacker, and we surround it by unreadable pages. So now if there's an injection of 0 into a pointer in the enclave, instead of going to address 0, which might be in attacker control, we go to address GS base plus 0, which is in the enclave, and the unreadable pages also stall any dependent loads. So that is a very nice protection against that, against arbitrary value injection. So how we did this was to make just all loads GS relative. For normal MOVs, that's a simple prefix of 1 byte, I believe. For complex instructions that do not take GS as a parameter, we need to replace those as well. So all of those was implemented in Clang 11. So an example of those is push, that implicitly uses the stack segment register that we don't have control over. So we need to replace the entire instruction with its components, basically. So we decrease the stack pointer and then write to it. So call has an included push. So you'll find here again the push in the call, and first a calculation of the return address. And then we jump to our target. And then we do the reverse thing for pop, and then return. So those aren't all the instructions that needed to be replaced, but some major ones. Okay, and it turns out that this actually works fairly well. So there's another mitigation called CISPA that was initially proposed for other transient execution attacks, and it works against pretty much everything because it places load fences everywhere, which means there's almost or very reduced out-of-order execution now at that point, and these slowdowns are huge. And for LVI, Intel is in light red, LVI opt, Intel proposed a better mitigation that removes most of these fences, but as we've seen before, these overheads are still very high. Our mitigation, on the other hand, in green, LVI-NULLify, as you can see, has very little overhead for virtually the same security guarantees. Some caveats, you'll have to read the paper for those. And if we zoom in here, we can see there's a third mitigation option, the CFI only, that just replaces returns, calls, and jumps. So that was also already in Clang. All right, so that already brings me to a conclusion. LVI-NULL is still here in Rocket Lakes, but those models don't have SGX anymore, so this isn't really a problem anymore. And the other models based on Ice Lakes don't even have LVI-NULL anymore, so those can have SGX. So what we didn't know at the time we wrote the paper, bad luck, is that the only CPU that is actually affected by this is the Comet Lake. So we're hoping maybe the implementation or the idea might be useful at some other time for something else. All right. And I think there's time left for questions.